I'm Dr. Chris Creighton, and in this video we'll be talking about radical functions. The core learning objectives are being able to find the domain, range, and intercepts of radical functions, along with graphing and evaluating them, and be able to determine if a radical is real or complex. So we're going to focus on the real or not real here, and later on we'll come back to complex numbers. So what is exactly a radical function? Well, in this case here, we're going to have the nth root of a is equal to b, and we're going to focus on what it means to be the nth root of a. So in this case here, this is equivalent to the statement a is equal to b to the n. So the nth root of a is whatever base b is that to the nth power gives you a. And so we say here that the number n here is the index / order. A is the radicand, and the whole thing here is the radical. So the radical is the nth root of a, where n is the index of order and a is the radicand. And this is equivalent to the statement a is equal to b to the n. And so we define a radical function as f of x is equal to the nth root of x. So there's a couple of common distinctions here. The one that we've already seen is the square root function. So the other values of n could be like the cube root, where n is 3, 4th root, 5th root, and so on. The one other thing I want to mention is that this is called the principal root. The nth root of a is the principal root. With n being even. That is due to if you have, for instance, 2 is equal to the square root of 4. If you translate this to the exponential, 4 is equal to 2 squared. 4 is also equal to negative 2 squared. That gives us two possibilities for the square root. Maybe negative 2 is equal to the square root of 4, or 2 is equal to the square root of 4. If you really want to define the square root as something that when you square it, it gives you the value on the inside of the radicand. So this one we don't use, and we say that this one here is the principal root. Now for odd roots, so n odd, there is only one root. So it is the principal root itself. So let's evaluate some of these. I find it very useful to translate these into exponential equations. So in this case here, we have the square root of 81. To figure that out, we can write that is equal to b. So then translating this into 81 is equal to b squared, we can probably see what b has to be. So in this case here, we're going to take the principal root and notice that 81 is equal to 9 squared. So being the principal root, having this 9 squared here, that tells us that b is equal to 9. So the square root of 81 is positive 9. It could very well be negative 1, but whenever you see a radical, it's always the principal root, which is the positive root. Over here, the 4th root of 256. Now that might be hard to think about, but translating it to the equation 256 is equal to 4, or b to the 4th power, figuring out what b has to be, we note that 4 to the 4th power is in fact 256. So then here, again, 4 is our principal root, so this value is equal to 4. Similarly over here, looking at this, the 4th root of 16 divided by 81, translating it, we get 16 over 81 is equal to b to the 4th power. So how can we write 16 over 81 as something to the 4th power? Well, the first thing I notice is that 16 is 2 to the 4, and 81 is 3 to the 4, which then combines as 2/3 to the 4th power. So then taking the principal root, because negative 2/3 also works here, the principal root then would tell us that this is equal to 2/3. So let's take a look at the 4th root of negative 16. So translating this is minus 16 is equal to b to the fourth power. And the biggest thing to note here is that b to the fourth power is always going to be a positive number. When you take a number to the fourth power, it's always positive. But here we're asking, is it equal to a negative number? That doesn't work. This has no solutions. There is no way to have some number to the fourth power is equal to negative 16. That is real. So in this case here, we're going to say this is not a real number. There is no way to solve b to the fourth is equal to a negative number, particularly negative 16. So later on, we are going to talk about how to solve this and find this value, and they're classified as complex numbers. So looking over here at the cube root of negative 8, maybe this one will work, maybe not. But here, we're going to say negative 8 is equal to b cubed. Now thinking about this a little bit, when you multiply three negative numbers together, it's still going to be negative. And I know that the cube root of 8 is 2. So this is, in fact, going with my gut here, negative 2 cubed. So looking here, I know that negative 2 times negative 2 times negative 2 gives me a negative 8. So then the cube root of negative 8 has to be equal to negative 2. This is an indicator that for odd indexed functions or odd order radicals, you can plug in negative numbers, and that is actually completely fine. And now taking a look at this last one, the negative square root of 36, this actually breaks into two parts. The first thing is I look at the square root of 36. I go, well, the square root of 36 is equal to 6. So I can plug that in. So this is negative 6. So that 6 comes from the square root of 36, and the negative is on the outside, and the outside is completely okay. So this value here is negative 6. So the two big takeaways here is that for even, these will be real numbers when you take the even root of a negative number. But for odd, you can take odd roots of negative numbers. So there's this little interesting feature going on here. So next we're going to start graphing these functions, because to graph them, the way we're going to do it is we're going to construct a table of values. The first thing though is we should try to figure out what the domain is. So we have a domain restriction, and this is due to an even root. So this is a square root, so this is an index 2. We have the restriction that x has to be a positive number, because as we saw with the fourth root or square roots, you cannot take a square root or a fourth root, a sixth root of a negative number. So our domain here is going to be 0 to infinity. You can only plug in positive numbers to that. So to graph this, we're going to construct a table of values. So I'm going to do x here, and then on the other side, we're going to do the square root of x. So in this case here, I'm going to plug in things that are square. So the reason why I'm going to do squares is because we don't really know a good way to evaluate what the square root of 2 is. That's not a nice value. So I'm going to choose things to plug in for x that I know what the square roots are. So for instance here, we're going to start with the beginning of our domain. Domain 0, because square root of 0 because it's 0. 1/4, the square root of a fourth, gives us a half, so that's a good value. 1, well, the square root of 1 is equal to 1, because 1 squared is 1. That's pretty nice. 4, square root of 4, well, that's 2. And then I'm going to do one more, 9. Square root of 9 is 3. So I'm choosing these values because they are squares. So our input x values are all squares. I don't want to choose 2 because the square root of 2 is some decimal number. Square root of 3 is also not nice. Square root of 4 is 2. Square root of 5 is not nice. So these are all relatively nice values that I can pick. So now plotting these, at 0 we have 0. At about a fourth we're up there at a half, so about somewhere in there. At 1 we're at 1. At 4 we're at 2. And then all the way out here at 9 we're at 3. So now playing connecting the dots, we see the graph of f of x is equal to the square root of x is this blue curve here, starting at 0, 0, or the origin, and extending outwards. So like the graph of the square root of x, we're going to graph the cube root of x. So f of x is equal to the cube root of x. So the one thing that we noted when we were evaluating things is that we could plug in negative numbers into the cube root. That is completely okay. So in this case here, the domain is going to be all real numbers, so negative infinity to infinity as an interval. There is no restrictions. And that's because we can solve for the cube root of negative numbers. Those things make sense. So in this case here, we're going to do x, and then we are going to do the cube root of x. So in this case here, the things that you should choose to plug in are going to be cubes. Because if you don't plug in a cube, like for instance, what's the cube root of 2? That's a little bit harder to figure out. But if I say 8, you can tell me what the cube root of 8 is. So I'm going to start plugging in cubes over here. So like for instance, negative 8, negative 1, because those are the next cubes, negative 1 over 8, 0, 1 over 8, 1, 8, and actually the next cubed is going to be a 27, so that gets a little big. But the cube root of negative 8, that is negative 2. That's what we found out earlier. The cube root of negative 1 is in fact negative 1, because negative 1 times negative 1 times negative 1 is in fact negative 1. The cube root of negative 1/8 is going to be negative 1/2, because negative 1/2 times negative 1/2 is 1/4, times another negative 1/2 gives you negative 1/8. The cube root of 0 is just 0, and then the pattern continues. Now these ones are just going to be mirrored but positive. So cube root of 1/8 is a half. The cube root of 1 is 1. The cube root of 8 is 2. And then the cube root of 27 is 3. Now if you notice, my scale on my graph doesn't go that far, but if it did, like double or triple in length, we would be able to get that point. So now I'm going to go ahead and plot these. So at negative 8, I get negative 2. So we're down here. That's our first point. At negative 1, we're at negative 1. At 1/8, so like somewhere in here, we're like right in there. And then at 0, we're at 0. And then at an eighth, we're like right in there. That's pretty close and accurate. At 1, we're at 1. And then all the way at 8, we're at 2. So this thing is much more stretched out. But it goes like this, and it goes like almost vertical in there, and it stretches out that way. So this is the graph of f of x is equal to the cube root of x.